A very good morning to Dr. Haikal and my fellow friends. We are from Chemical Engineering Thermodynamic, ECH3120. So today we are going to present a topic which is thermodynamic properties of phases, which is two-phase system. So I'm presenter number one, which my name is Krishna Annaprapun Anand. My metric number is 201734.
My name is Lim Sumin, metric number 203692.
I'm Luining. My metric number is 200468.
My name is Pavita Jayakumar and my matrix number is 197581.
Hello, my name is Muhammad Amir Irfan bin Zafarin and my matrix number is 200681.
Hi, my name is Aiman Hakimi Berizal. My matrix number is 202586.
Next slide. Next slide. Next slide.
Can you see this slide?
Yeah. So, firstly, we are going to talk about behavior of two-phase system. So before going into that, we need to know what is phase. Phase is a quantity of matter that is homogeneous throughout. So the diagram over here shows us the two-phase system in contact with constant temperature heat reservoir. And the graph over here is PT relation for liquid and vapor system. So next.
So now I'm going to explain about the two-phase system, which is the curved loops. So this region is in which liquid and vapor can coexist, bounded by the liquid saturation curve on the left. As you can see, it is the left. And then the vapor saturation curve on the right. This is roughly dome-shaped, so we can call it as a dome shape. And this often referred to as a vapor dome. So we can call it as a dome shape or either vapor dome. Outside of this region, the equilibrium state will be in a single phase. The regions of the diagram in which the system will be in liquid and vapor phase respectively are indicated. So only under the dome, we have two phases. The stiffness of the isotherms in liquid phase is due to the small compressibility of most liquids. So as you can see on the right side, on my left hand side of the graph, you can see the phase for the liquid phase is quite narrow. The behavior of isotherms at temperature below the critical point, this is the critical point, the pointing over here, in the region to the right of the vapor dome approach those of an ideal gas as the pressure decreases. So you can see the line over here. And the ideal gas relation is good approximation in this region. Next slide. At a high enough temperature, specifically at a temperature corresponding at the pressure at the peak of the vapor dome, as I mentioned earlier, at the point where there is a critical point, there is no transition from liquid to vapor, and fluid goes continuously from liquid-like behavior to a gas-type behavior. So in this zone, where, as I said, from the dome, there are two phase exist, which is liquid and vapor. Okay, so there is two bounding situation where when the last trace of vapor condenses, the state becomes saturated liquid, which is on my left hand side on the previous graph. And when the last trace of liquid evaporates, the states become saturated vapor, or we can also known as dry vapor, which was on the right hand side in the graph. So if we put more heat in the saturated vapor, as we all know, it becomes a superheated vapor. So I'll pass the slide to the next presenter.
So, all right, now I'm going to explain about the constant pressure curves in TV coordinates showing a vapor dome. So, first of all, we need to know the inside the vapor dome. The constant pressure lines are lines of constant temperature. So, it is very useful to describe the situations encountered as if we decrease the temperature, the pressure, or the equivalent increase the specific volume, the starting from a high pressure to like low specific volume state. As a result, the behavior in the upper left-hand side isothermal region is like liquid with a little compressibility. As the pressure is decreased, the volume changes little until the boundary of the vapor dome is reached. So once this occurs, the pressure is fixed because the temperature is constant. As the piston is withdrawn, the specific volume will increase, so more liquid will evaporate and more vapor being produced. Now I'll pass to the next presenter.
So I will continue with the graph about the specific volume at constant temperature and stages within the vapor dome in a liquid vapor system. So usually during the process of in the phase of saturated liquid vapor mixture, since the expansion is isothermal, and heat is transferred to the system, the specific volume will increase at constant pressure until the left-hand side of the boundary of the vapor dome is reached. At this point, all of the liquid have been transformed into the vapor, and the system again behave as a single-phase fluid. For water at temperatures near to the room temperature, the behavior would be essentially that of a perfect gas in this region. And then for to the right of the vapor dome, as mentioned above, the behavior is qualitatively like that of a perfect gas. So I will pass to the next presenter.
So I will explain about the hypothetical process pathway. In order to calculate the enthalpy changes, we need to use the hypothetical process pathway, in which to construct the process pathway, we need 2 points, which is the starting point and the end point. The starting point is the point that we define the reference state, like the phase, the temperature, and also the pressure. And the endpoint is the condition that the stream of the interest. So there is the example of the hypothetical process pathway. So by construct the hypothetical process pathway, we can uh, we can calculate the enthalpy changes that we want from the from the start from the starting point to the end point. So next. Since internal energy and enthalpy are state properties, any convenient process path from a reference state to a process state can be chosen. The state properties value are independent only on the state of the species, like the phase, temperature, and also the pressure, and not how they got there. Next. Okay, the ideal process path will allow you to make use of the sensible heats or the heat capacities, phase transition temperature, and also the latent heats. All the data for these properties, we can find it in the properties table, which is already identified by the through experiment. Okay, I'll pass to the next presenter.
Next slide. So for example and problems, we have made a question which is calculate the enthalpy change as 1 kg of ice at 0 degrees Celsius is transformed to superheated steam at 400 degrees Celsius at 10 atm. So next. As stated by Ami just now, we have to use this method called hypothetical pathway. But before we use that method, we have to specify our reference state first. So which in this case, we specify our water as solid, in solid at 0 degrees Celsius and 1 atmosphere. So first of all, the hypothetical pathway will move the water into liquid state first at the same temperature and same pressure. So in this case, the H1 will be the Hm, which is the enthalpy at the normal melting point, which can be found in the table B1 in the Felder's chemical processes book. And next is the temperature switch, which we can see at the H2, the temperature shift from 0 to 100. So in this case, to calculate the H2, we have to use the specific heat expression, which also can be found in table B2 in the same book, where we just integrate the expression of specific heat in terms of the temperature, which in this case 0 to 100. And for H3, you can see H2O is moving from liquid becoming a vapor. So H3 will equals to the specific heat of the heat of vaporization of water, which can be found in table B1. And for H4 is again the shift of temperature from 100 to 400, and we can use the same expression of specific heat, but this time we use 100 to 400 degrees Celsius. And lastly, for H5 is the shift of the pressure, where from 1 atm becoming 10 atm. But in this case, H5 is approximately equals to 0 because we assume that the pressure is small changes in the system which won't affect much on the enthalpy, so we can assume it as 0. So lastly, we just add H1 till H5 and we got the enthalpy of H2O in solid becoming H2O in vapor at 400 degrees Celsius and 10 atm, which is 3,612 kilojoule per kilogram. Next. So I guess that's all from us. I hope whoever is watching this understood whatever we said in the video, and hope you guys learned something. So thank you.